Okay, what do we have here? Well, a new type of two-stroke internal combustion engine, in which the pistons are not driven by a crankshaft, but where instead two pairs of pistons rotate around a single point and well in opposite directions. The back and forth movement of the pistons around the center is converted into rotary motion via connecting rod and gear. We slow the engine down some more to see what is actually happening here. This construction offers a number of advantages, including less friction and a better air exchange of the cylinders. But there are more advantages that will be discussed. Now, if we zoom in on the air exchange first, there are two ports in each of the cylinders directly opposite each other, and they are opened by the pistons. The incoming air does not have to make a 90-degree turn and flows straight from the intake to the exhaust ports. The exhaust port opens first, allowing the remaining pressure to cause an expansive outflow, creating negative pressure in the cylinder. When the inlet port now opens, fresh air is sucked in by the negative pressure. It can also be clearly seen that the working stroke and the compression stroke occur in this engine at the same time. Before we go further into the advantages of this engine, let's call it the rotary engine. We are first going to look at normal internal combustion engines to see why they only have an efficiency of about 40%. In existing internal combustion engines, expansion, compression, and inertia forces create friction in all pivot points, and friction between piston and cylinder wall. The force created by the expansion stroke goes through 3 pivot points to crankshaft, and the force required for compression goes from crankshaft again through 3 pivot points to piston. In a 4-stroke engine, there is also the coil and intake stroke, so the mechanical losses of, for example, a diesel engine are around 8%. Because in existing engines, there are large forces between piston and cylinder wall, oil lubrication is necessary here. However, the greatest losses in existing engines are caused by heat loss, overall about 50%. Of this 50%, 20% is caused by forced back cooling of the engine, and the other 30% by heat loss through the exhaust. If we now look back at the rotary engine, what friction occurs here as a result of expansion, compression, and mass inertia forces. First, two pistons form one cylinder pair. The forces on one piston therefore acts directly on the other piston, without intervention of pivot points and thus without friction losses. Compression and labor stroke occur at the same time. A part of the force from the labor stroke of one piston is directly applied to overcome both forces of A, the inertia force of the piston pair, and B, the compression forces that work at the same time on the other piston. In this engine, no forces occur between piston and cylinder wall. However, all the force from the work stroke that are used usefully move through the pivot point in the center to the connecting rod. This graph globally represents the forces which have just been discussed and which occur in the engine. The blue and red lines show the forces progression in both cylinders. If we follow the blue line, the negative forces represent the compression stroke, the positive forces the working stroke. The gray line represents the mass inertia forces acting on the piston pair. If this line is negative, then a force acts on the piston pair to accelerate it. If the forces are positive, then the piston pair slows down and thus releases a certain force to overcome, for example, the compression forces. The colored graph clearly shows that part of the expansion stroke are converted into mass inertia forces, and also that these forces are then, in turn, used to overcome the ever-increasing compression forces. The center of gravity of the piston pair belongs exactly in the middle, and because of this, the centrifugal forces cancel each other out and cause therefore no friction losses. If the engine were equipped with only one piston pair, the inertia forces would cause an imbalance in the engine. With two equal piston pairs making exactly equal motion in opposite directions, however, the inertia forces cancel each other out also. This animation shows for clarity the movement of one cylinder pair. The mass inertia caused by the connecting rods are compensated by the gears, which also fulfill the function of balance shafts. Furthermore, it can be seen clearly that the back and forth movement of the pistons around the center is transferred to rotary motion through 4 pivot points. Only 2 of these pivot points complete a full circle. With a double-acting piston pair that moves opposite to each other, both centrifugal and inertia forces cancel each other out. The 2 piston pairs with associated frame are identical. They are only rotated 180 degrees with respect to each other on the same shaft. The manufacturability of the piston pairs is a subject that deserves its own presentation. Because the pistons do not have to come into contact with the cylinder wall, oil lubrication is not necessary. This increases the choice of materials to be used. All this is important for the reduction of heat losses, a subject that will be discussed next. The Sankey diagram shown is of a diesel engine and shows that roughly 50% of the energy value from the fuel is lost. 20% through back cooling of the engine and 30% because of the heat that's leaving the engine through the exhaust. The proposed solution for this problem in brief is as follows. By using heat-resistant and rust-proof materials for piston and cylinder, higher operating temperatures are possible. At the same time, the engine can now be cooled down by water injection during the working stroke, such that the exhaust gases leave the engine be half in temperature, thus from the current 800 to about 400 degrees Celsius or even lower. The temperature reduction during the work stroke brings no pressure drop because of the volume increase that occurs during the conversion of water to steam. Looking first at a possible increase in operating temperature, it can be seen that the pivot point closest to the pistons is located in the center of the engine. This pivot point has already a considerable distance from the heat source, and because it needs dynamic oil lubrication, it can also be cooled. The other pivot points on the gears can be isolated from cylinders if needed. The water injection under high pressure could take place during almost the entire working stroke, in such a way that only a minimal amount of heat energy is lost. Since the exhaust ports are at the bottom of the cylinder, any condensed water will be blown out of the engine. How far with this method the engine can be cooled back without compromising the power output is a subject for the next presentation and follows if there is a sufficient interest. For now, a final overview of the proposed construction, and if you find this presentation interesting, give it a thumbs up.